All right, so here's quiz 8. Um, Problem 1, this will be how I phrase things on a test question. I give you a couple series to evaluate or to determine if they converge or diverge. And I don't tell you exactly what method to use, but I do tell you to narrow it down to a comparison or limit comparison. Okay, so it says to use a comparison or limit comparison to determine if this series converges or diverges. So in that case, we look at our sequence, and what I want to do is find a simpler sequence to compare this to, and I do it usually by picking out the most powerful term from the top and the most powerful term from the bottom and ignoring everything else. So the top is 7 to the n. Can't make that any more simple. Bottom, 6 to the n is bigger than 2 to the n, so I take that 6 to the n and ignore the 2 to the n. Okay, so now I have a simpler one. This simpler sequence is just geometric. It's 7 over 6 to the n. And the point is, geometric series, the summation of that, we know what it does. All right, so now I have to do one of two things. Either I need to find a direct comparison between these two, and so let's think of it if we can do that. This one, the one with the bigger denominator, the more complicated denominator, 6 to the n minus 2 to the n, that denominator is smaller than 6 to the n. We're dividing by a smaller number here than we are here. So if we're dividing by the larger number, that makes the fraction I don't remember how I phrase it. This one has the smaller denominator, so it's the larger fraction. So this one is bigger than this. All right. So that tells us our unknown series will be bigger than the series formed with this sequence. And so let's go back and describe that. This is a geometric series. Its ratio is 7 over 6. That's bigger than 1, so this is divergent. Because 7 over 6 is greater than 1. Or really, 7 over 6 is greater than 1. All right, so we've successfully made a comparison. We know what the simpler thing does. It's divergent. Now, since we're using a direct comparison, we have to carefully ask ourselves, is our comparison useful in this context? So this tells us our unknown series is bigger than a divergent series. Bigger than divergent, that's like bigger than infinity, that's still infinite. That's still infinity. So if it's bigger than divergent, it's divergent. Now, just for discussion purposes, if this was 6 to the n plus 2 to the n, I'd still try to compare it with 7 over 6 to the n. But then the comparison would flip. If I had a larger denominator here, this fraction would be smaller than this fraction. And smaller than divergent doesn't help you. So in that case, you'd have to use the limit comparison like we'll do on the next one. All right, so let's do the second one on part 1. So we have summation of this rational expression n squared plus 7n plus 9 divided by 3n squared minus n plus 8 I screwed this one up when I wrote it. I'm just now noticing, but that's all right. I'll make up a separate example to do what I meant to do. All right, so I made up the wrong example here, but we can still, I guess, technically do it with a comparison or limit comparison. The right way to do this one, however, would just be the limit of this sequence is 1/3. It's n squared over 3n squared. That's not 0, so the divergence test tells us this is divergent. All right, so, but if I if I'm forcing myself to use a comparison or limit comparison for this, our thought process is just what is the simple sequence that this is most similar to? Again, take the most powerful term from the top and the bottom. That would be n squared over 3n squared. That simplifies to just be 1/3. Summation of 1/3 as an infinite series, that would be divergent. So we're trying to compare this to a divergent series, but this time I can't easily come up with a comparison. So we could probably come up with a comparison that works eventually for large enough n, but it's not worth it. If you can't easily come up with a less than or greater than here, then use the limit comparison, and that was the limit of one of our two series, or one of our two sequences divided by the other. So n squared plus 7n plus 9 over 3n squared minus n plus 8. Then divided by this would be 3n squared over n squared. I guess I could go ahead and cancel the n squareds. And so that's going to be the limit of 3n squared plus 21n plus 27 over 3n squared minus n plus 8. That limit's going to be 3 over 3, because n squared over n squared. So 3 over 3, which is 1. And so if you remember, the successful condition for a limit comparison, if I'm using the limit comparison test, I look at this limit. If I get an answer which is not infinity and not 0, so any number between 0 and infinity, but not the endpoints, not 0, not infinity, that's a successful limit comparison. That tells me that the behavior of my unknown series matches the behavior of my comparison series. So since this one diverged, this one will diverge. Divergent. All right. So that's how you would do this one with a limit comparison. But like I said, that's overkill for this example because this one fails just by the divergence test. What I should have done is leave off the n squared, I guess. Let me make up a similar problem. So just put like 7n plus 5 on top and 3n squared minus n plus 8 on bottom. So same idea. We want to compare this to something. So you to get the other series, you just ignore the lower degrees terms. Take the largest degree from the top and the largest degree from the bottom. That'd be 7n over 3n squared, which simplifies to be 7 over 3n. So that's basically the harmonic series, just with an extra coefficient. So 7/3 times the summation of 1 over n. That's a divergent series. That's an n. That's divergent. But again, I can't quickly get a comparison. Again, I might be able to if I say if n is large enough, this is bigger than this. That's probably true. But it's not simple to do. So if you don't quickly get a comparison, just do a limit comparison. So take the limit as n goes to infinity of 7n plus 5 over 3n squared minus n plus 8 times the reciprocal of the other one, so 3n over 7. And so then if you simplify that, you have the limit of 21n squared plus 15n over 21n squared minus 7n plus 56. But it's n squared over n squared, so the limit's 21 over 21, which is 1. Our answer to the limit is not 0, it's greater than 0. So that tells us it's a successful limit comparison, so our unknown series matches the behavior of our known series. So this is divergent. All right, so apologize again for messing up on the problem and not catching it before I posted it. Let's move on to problem 2, which is to use the ratio test or the root test to determine if the series are convergent or divergent. So here I'm telling you, you have to use the ratio test or the root test. Summation of 4 to the n squared divided by n plus 1 factorial. All right, so like I've said before in the lectures, ratio tests and root tests are kind of go hand in hand. If one of them works, the other one technically will also work. If one of them fails, the other one will also fail. So it's just a matter of picking which one is easier for the given series. If you've got an n factorial or something similar, chances are the ratio test is easier. In general, the root test is better if you've, well, in general, the root test is best if every factor in your sequence has a power of n, as something raised to the nth power. So if it's just 4 to the n and n to the n, that'd be a root test situation. But factorials, if I need to take the nth root of a factorial, that's going to be a mess to try to deal with. Even n squared, taking the nth root of n squared, that'll be a little bit more of a pain than doing a ratio test. So root test is only preferable in a very, very narrow kind of situation where every single thing in your sum is either a constant or something raised to an nth power. So really, the ratio test should be your default, unless you specifically think the root test would be easy in that given situation. You default to ratio test unless root test is obviously better, essentially. All right, so let's do the ratio test. This is looking at a specific limit. In the ratio test, what we do is we have to take the absolute value. Then we're going to write the same expression, but with n plus 1 plugged in for n everywhere. So 4 to the n plus 1 times n plus 1 squared divided by n plus 1 plus 1, so that's n plus 2 factorial. And then we multiply that by the reciprocal of what's already there. So we're going to multiply by the reciprocal of this. That's n plus 1 factorial divided by 4 to the n times n squared. All right, then in the ratio test, we tend to do a lot of cancellation so that you cancel corresponding pairs. 4 to the n plus 1 divided by 4 to the n. Well, there's one extra 4 up here. So subtract the exponent, n plus 1 minus n. That gives me 4. Do the factorials next. N plus 1 factorial divided by n plus 2 factorial. N plus 2 is 1 bigger than n plus 1. So if I cancel, these have all the same factors except for the n plus 2 has one extra factor, n plus 2. And then the polynomial part, n plus 1 squared divided by n squared, that doesn't cancel, but that's n plus 1 over n quantity squared. And now we're asking, what is the limit of all this stuff? Well, as n goes to infinity, n plus 1 over n, that just goes to 1. Because it's the same degree with leading coefficients 1 and 1. So this part goes to 1 squared. The remaining stuff is 4 over n plus 2. As n goes to infinity, that goes to 0. 4 over infinity is 0. So my limit's 0. And then in the ratio test, we have a successful ratio test if, well, I guess it depends on your perspective. Ratio test tells you that it converges when your answer is less than 1. So 0 is less than 1, so this is convergent. If your answer comes out to be bigger than 1, that tells you it's divergent, which is still a successful test because it's telling you what's happening. So if your limit is bigger than 1, you get divergent. The ratio test fails when your limit turns out to exactly equal 1. In that case, it is inconclusive and it doesn't tell you anything. Right? All right, so one more. Summation from n equals 1 to infinity of 1 minus 2n over n plus 5 raised to the 3 times n power. Again, we still have the directions to use the ratio test or the root test. Again, our default choice is ratio unless root test seems easier. And in this case, it definitely does, because what we have here is some expression, all of which is being raised to an exponent involving n. So the root test involves taking the nth root of something. Taking the nth root is going to cancel that n in the exponent. So that's going to make things a lot easier. I could probably do a ratio test, but it's going to be a mess to try to simplify. It'll probably involve using L'Hopital's rule at some point, and I don't want to do that. So the root test says we take the limit as n goes to infinity of the nth root of the absolute value of this inside stuff. Okay, the nth root, that's just dividing my exponent by n. So this is going to give me the limit as n goes to infinity. It won't take care of the absolute values. I have to keep those absolute values. So absolute value of 1 minus 2n over n plus 5 to the third power now. So 3n divided by n leaves me with 3 in the exponent. So now let's think about what is the limit of this. You don't have to multiply things out. Just take it step by step. Inside the parentheses here, that expression is an n over n polynomial. So I take the ratio of their leading coefficients, negative 2 divided by 1. So I have negative 2 to the third power, and that's inside of the absolute values. So negative 2 cubed is negative 8. Absolute value of negative 8 is positive 8. So the answer to my limit is 8. 8 is bigger than 1, and just like with the ratio test, if our limit's bigger than 1, that tells us divergent. The conditions are the same as the ratio test. So if the answer was less than 1, we'd have convergent. Bigger than 1 is divergent. Equals 1 is inconclusive. All right. So as usual, if you have questions about any of these or need extra explanation or clarification, send me an email and we'll figure out the best way to discuss it. All right, that's it.